Folks, welcome to Rational Science, the only site on the internet that does physics. What does everybody else do? They do mathemagics. What is mathemagics? Well, mathemagics is the movement of concepts. That's what it is. All the explanations, all the physical interpretations involve the movement of concepts. They vibrate concepts, they move them around, they transfer concepts. They're all concepts. And we don't do that in physics. In physics, we do one thing and one thing only, and that is move objects. So today we're going to be analyzing, following what I did last week, we're going to be analyzing Einstein's I always say 2017, no, it's 1917 book, okay, 100 years ago. His book where he summarized essentially all the thought processes he went through to get his theory of general relativity. First special relativity and then general relativity. Okay, I covered the introduction the other day, and so today we're going to be talking about two specific things that Einstein mentioned in that book. And the first one is field. We're going to talk about Einstein's field. Remember, it's a field equation, the one he came out with in 1915. And we're going to talk about the principle of equivalence. Does the principle of equivalence have any validity? Okay, and how did he justify it? Okay, that's what we're going to look at today. So if you've got something better to do, well, don't do it. Stick around. You might learn something. Okay, let's get started. This is more or less the introduction. The part on the bottom is what he wrote in his preface. He says, an exact insight into the theory of relativity to those readers who, from a general scientific and philosophical point of view, in other words, he's going to talk about what? Philosophy, or what people dismiss today as philosophy, giving you a physical interpretation why general relativity and special relativity, for that matter, were necessary, how he came up with all that. So he's going to talk about what Wikipedia says, explaining the theory, okay? Forget about the math. We don't care about the math. What the physical interpretations, what was going through his mind, okay? That's what he's going to talk about. And he does it for the average educated person, right? Layman. Okay, so that's how he starts. I did discuss the other day that there were other people involved. You know, the only name that survives today is Einstein. It's a synonym of intelligence, which is questionable. But there were other people involved in developing special relativity, and from there, Einstein developed general relativity, okay, which is a gravitational theory primarily, okay. So what does Einstein say regarding the field in his book? Okay, we're going to talk about his book, and one of the first things he mentions, I can't see the first thing, but he immediately introduces the field. And before he does that, he's going to justify why the field, okay? And the issue is that he's saying that there is no such thing in physics as action at a distance. You know, until then you had Newton, you had all these people all the way to the 20th century, beginning of the 20th century, and they said, well, action at a distance, like gravity and so on, or electricity or magnetism. How does it do its magic from far away? And Einstein said, look, there's no such thing as action at a distance. So let's get that first clarified there. It says the success of the Faraday-Maxwell interpretation of electromagnetic action at a distance resulted in physicists becoming convinced, okay? Talking about people at the beginning of the 20th century, right? Convinced that there are no such things as instantaneous action at a distance, not involving an intermediary medium of the type of Newton's law of gravitation. Okay, according to the theory of relativity, action at a distance with the velocity of light replaces instantaneous action at a distance of action at a distance with an infinite velocity of transmission. This is connected with the fact that the velocity c, little c, right, velocity of light, plays a fundamental role in this theory. as a result of the more careful study of electromagnetic phenomena, we have come to regard action at a distance as a process impossible without the intervention of some intermediary medium. What is he saying? He's saying the following, and you got to get this straight. A lot of people you read today, mathematicians primarily, or people who try to translate what the mathematicians do to the lay public, right? They bring it down to their level. And what you'll hear a lot about there, people write and they say the reason Einstein's theory replaced Newton's, because it was a little more accurate, a little more precise than Newton's theory. And specifically, they're talking about the fact that they applied it to the orbit of Mercury. And they said, look, Newton's equation does not really explain that, or does not describe Mercury's orbit precisely. There's always a little bit left over. And Einstein did not account for all of it, but accounted for more of it than Newton. And because of that, they dumped Newton. So the story goes, right? They dumped Newton and they said, we go with Einstein. No, the reason was what he just says here. The main reason all the mathematicians today believe in this nonsense, okay? They switched over from Newton to Einstein as far as, when you get to the nitty gritty, is because they could not reconcile special relativity, the speed of light, with gravity. Newton's equation says gravity acts instantaneously. You move an inch, the distance changes, immediately you have a different weight. That's what Newton's equation says. And Einstein said, well, nothing can travel faster than light. In fact, other people have said it before him. And special relativity especially is based on the notion that nothing can travel faster than light. They invented later on tachyons and faster than light travel, all that stuff, but and that's in the literature, by the way. But they downplay that. They said, special relativity is still strong, okay? They all believe in special relativity. But if you believe in special relativity, you can't accept Newton, because Newton says instantaneous, and Einstein says you can't travel faster than light. That was the big problem. That was the major problem. So everybody switched over and said, no, we're going to believe in special relativity. They went with mathematics and forgot about the physical interpretations. Okay, they cleaned their nose holes with physics. They said, we're going to do math here. We're going to do everything with math. And that's what happened. They switched over because of the speed of light. That was the issue. And Einstein saying that there, action at a distance is a little, first of all, it's instantaneous. That's a problem. Then we couldn't see the mediator. And so he said, hey, I got a mediator. Oh, what's your mediator? Well, it's the field, as he's going to say. It's this space-time. That's the mediator. Everything works through space-time. And so not only did he present a mediator, but he said it's not instantaneous. And so today they have the irrationality out there, theory, that if the sun were to disappear, right, gravity would take 8 minutes to reach us. That we would find out about it 8 minutes later, not only because the light would take that long to come to us, but also we wouldn't feel anything. We wouldn't feel anything instantaneous, as Newton's equation suggests, that suddenly the Earth goes flying out of the solar system because there's no sun to hold it within its grasp. That's the notion we have today. What's interesting about that, here we have Einstein saying you need a mediator, and later on came another fellow, his name was Richard Feynman. He says something totally different. He says many physicists used to say that direct action with nothing in between was inconceivable. It is impossible that there can be a force with nothing to transmit it. But what really happens when we study the direct action of one piece of matter right against another? We discover that it is not one piece right against the other. They are slightly separated, and there are electrical forces acting on a tiny scale. Thus, we find that we are going to explain so-called direct contact action in terms of the picture for electrical forces. it is certainly not sensible to try to insist that an electrical force has to look like the old familiar muscular push or pull, when it will turn out that the muscular pushes and pulls are going to be interpreted as electrical forces. In other words, he says, look, action at a distance is a problem, in any theory, but he says, we have to get used to the fact that there's action at a distance with nothing in between, because even in the case of things like, electrical forces or action of an atom against another atom, there's still, some forces in there, right, that you have to account for even at that level. So you always have these abstract concepts, and he says, we don't like it, but we have to accept it, that everything works through these concepts. And so, what I think Feynman was saying is, that he's going to do voodoo physics, he's going to pinch the little doll and it's going to hurt you. And he says there's nothing in between because, even if we were to put atom against atom, push, surface against surface, even there you have a force, a field, or something that interacts. And so we can't avoid the abstraction. That's what he's saying. So Feynman was suggesting voodoo physics, okay? And what did Einstein propose? He said you need a physical mediator, but what did he propose? Well, here he is saying it in his book. If, for instance, a magnet attracts a piece of iron, right, we cannot be content to regard this as meaning that the magnet acts directly on the iron through the intermediate empty space, okay? So what does he propose? He says, but we are constrained to imagine that the magnet always calls into being what? Something physically real in the space around it. That's something being what we call a magnetic what? Field. So he's saying that a field is a thing, okay? And he's going to do his gravity with this field thingy, okay? But he's using the analogy of what happens in magnetism, that, you don't see anything there, you can't touch anything. As far as we're concerned, there's no mediator, but we call that mediator, or that medium, that intermediary, that agent, we call it a field. Okay, that's where the problem is. These people are turning a field into a physical object, and the question is whether that is valid in physics. In religion, yeah. In ordinary speech, perhaps. Not in physics. But he's saying it is. That's what he's going to use. He's going to use the field. That's where the field theory comes of general relativity. In its turn, this magnetic field operates on a piece of iron. So he's going to use the field to operate, to spank the piece of iron. That's what he's going to use. He's going to use the field. Okay, so that's what he's proposing. Then he says the Earth produces in its surrounding, he's using it now as an analogy for gravity, a gravitational field which acts on the stone. So he's going to use now the field to act on a stone. He's going to use the field as a baseball bat. Okay, that's the problem. And so it's important, to get a handle on this word field, because that's what he's going to use. And Feynman also had something to say about that, and here's what he's got to say. He says, the best way is to use the abstract field idea. That is, that it is abstract is unfortunate, but necessary, okay? The attempts to try to represent the electric field as the motion of some kind of gear wheels, or in terms of lines or of stresses in some kind of material, have used up more efforts of physicists than it would have taken simply to get the right answers about electrodynamics. What is he saying? He's saying, look, so both Einstein and him are both right and both wrong. Einstein is right when he says we need a physical object as a mediator. You can't do action at a distance. You have to have something in there, okay? Feynman says, no, you don't, because even when you get to the atom against atom, you got a field, you got a force, you got something in there that is abstract, and final interaction is going to involve a concept, an abstract concept. Okay, that's the answer that Feynman essentially gives to Einstein. So Einstein says, look, I'm going to put an object, I'm going to put a thing in there. I'm going to put a field. And that's where he's wrong, but this is where Feynman is right. And he says, look, a field is an abstraction, but we have to accept it as an abstraction, and we're going to use this abstraction to do physics. Okay, so they're both right and they're both wrong, each one in different aspect. Einstein is right when he says you need a mediator. Feynman says is wrong when he says that you don't need a mediator. Einstein is wrong when he says a field is a mediator, and that's what he's going to use. And Feynman says, well, I recognize that a field is an abstraction, but we have no choice but to use this thingy we call field to do our physical interpretations. Okay, so this is where we're at. This is where the problem is with this word field. It's pervaded mathematical physics, and everybody uses this word field. We talked about it a little while ago, a couple of weeks ago, about the fact that they introduced quantum field theory. Well, you can't do that because you got an oxymoron in that term. Quantum means discrete, and field means extended. And so they covered all the bases. They said we have a discrete extended. that's how they fixed the problem. They covered all the bases. They went the best of all worlds. And that's where we're at today as far as physical interpretations. And of course, at the end of it, even Feynman said, nobody understands quantum mechanics, and they've given up on physical interpretations. They give it to the philosophers, and everybody says, oh, that's philosophy, Bill. You're talking about philosophy. No, it's known as physics. And they were trying to do physics throughout hundreds of years, but finally they threw in the towel. They said, we cannot explain it. Don't ask us anymore. We do math. And then when they do the physical interpretation, it's all irrational. When you question that, they say, well, go to the other guys on the other side of campus, ask the philosophers, because we don't do that. We just do equations. So why did they even attempt it? Why did they even try to give a physical interpretation if they don't understand it and they know it's irrational and it's not part of their job description? Why are they still trying to give you physical interpretations? In fact, that's all that the celebrities of physics, people like Tyson and Hassenfelder and Carroll, all these people, all they do all day long is physical interpretation. They don't put equations out there. They give you the layman's version of what they do in math. And when you question that and say it's irrational, they say, yeah, we know it's irrational. We don't understand it either. Go to the other side of campus. Okay, so here we have good old Arvin Ash. I talked about him in the past, and he's going to tell you what a field is. He's really going to make it physical. That's what he's really doing here, because he's saying, look, a particle is the vibration of a field. It's the excitation of a field. You say, hold it, excitation of a field, that means a field is a thing. In fact, he draws it as a thing. He draws it as a canvas, right, as some kind of mat there. And he says the vibration produces this hump, which is not an island, it's a peninsula, right, aside from that. But the particle is the vibration of the field, meaning if a particle is something, solid that hits things and interacts with things, and it's the vibration of the field, then the field is a thing. Okay, so again, they're treating it as a field. They draw it as illustrate it, right, as a field, as a thing. I think there should be no doubt. And then, when you question that and say, well, what is that? What are all those little, what is it? Why does it look like that field? Well, what you're staring at is a bunch of number lines. That's what it is. All those little lines, those are number lines. They're vibrating the number lines, calling that a field, because what is a field? A bunch of numbers, right? A value at each point in space. They're taking all these values, they're vibrating them, turning it into this canvas, and with this, they're trying to give you a physical interpretation of their math. It's all irrational, 100% of it. And so let's listen first, just so you know that I'm not putting words in their mouth. Let's listen to good old Arvin Ash. He's the guy who's going to talk about his own field. Okay, so let's listen to him, see what he's got to say. Here goes.
All these fields extend out in all of space-time. In other words, the fields are always there and exist everywhere, including inside your body. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum.
Okay, so is a field a physical object? Is it a thing? Well, according to Arvin Ash, it is a thing. It's inside your body. It's everywhere. So what is this thing that it exists and is inside your body and everywhere? Isn't that a thing? I mean, he's not talking about love. He's not talking about intelligence or consciousness. He's talking about a thing. He's saying, look, this is everywhere, okay? And so we have to find out what this field thingy is to see if Einstein has any validity whatsoever to use it as an object, or Arvin Ash, any of them. At least Feynman admitted that it's not a thing, it's an abstraction, okay? But not all mathematicians realize that or say it that way, okay? So this is what you find when you look up what a field is. 3 irreconcilable notions of field. One is a value at each point in space. That's the formal definition, okay? That's what you'll find out there. And a value is not a thing, okay? It's a number with a unit or whatever, right? So you can't say that if that's the definition of field, you cannot say that's a thing. A number is not a thing, not in physics, okay? In ordinary speech, is a separate issue. At the same time, it's a region with invisible activity. You know, when Faraday created the word, he's the guy who invented the word field, by the way, in the 1830s. He was referring to a region like between two magnets. He said there's something there I can't see or touch, but it has some action on iron filings or whatever. And so he said there's some activity going on in there. I'm going to call that region a field, okay? And so it's a region. The field is not a thing. A region is not a thing, okay? And so he's saying, look, there's something in there, some activity, and we're going to call that region, that thing that we can't see or touch there, we're going to call that a field. And then there's the, there you have some examples, by the way. And then you have the baseball bat version of field. It's an object, it's a thing, which is how Arvin Ash used it. It's also how Einstein used it. They used it as a thing. They said, we're going to hit it with a field. No, field is a bunch of numbers. It's a bunch of values at each point in space. You can't take values and say, I'm going to hit a ball with that. And that's where the problem is. They're treating it as all three of them. They use the word field as all of the above. It's not like they choose one over the other. No, they use all three of them depending on the context. And that's where the problem starts, because you know you can't use a concept as an object, as a thing, which is what these people are doing. And so let's find out what a field is. What a region is. Let's see if that's valid at all, okay? And region is not a thing. A lot of people seem to think that it is, so I need to clarify that, okay? This is known as a hand. I hope all of you are familiar with your hand. You know, just point it out there and you'll see it, okay? And that's a hand. But if I want to talk about the palm of the hand, okay, here's the palm of the hand, okay? Palm of the hand is a region of the hand. It's not the hand. It's not the same thing as a hand. It's a region of the hand, okay? Let's get that straight, okay? If you want to talk about is a region an object? No, it ain't, okay? Is a palm an object? Yes and no. If it's part of the hand, it's a region. It's a region of something else, and that something else is the hand. If you want to talk about the palm as a physical object, then you have to sever it from the hand, okay? You got to do this. You got to cut the palm. You got to cut the fingers off. Now it's a standalone object. Now you can say it's the palm. Now I'm going to talk about the palm as a thing. I can move it. I can do whatever I want. Otherwise, I'm moving the hand, not the palm, okay? Palm is a region of the hand. If I want to talk about the palm as an object, as a standalone object, I got to cut the fingers. Sorry. You know, no way about it in physics. Again, in physics, not in ordinary speech, not in poetry or whatever, okay? Okay, so a region is not a thing. It's not a standalone thing. A region is always of something else. A lot of people don't realize that. They treat region as a thing. Like, black hole is a region of space, they say. Well, if it's a region, it's not a thing. Okay, and region can't move stars around. Okay, for example, right? So again, they use that region and field notion anytime they want to. They introduce it in there because they want to get away with murder in their physical interpretations. Physics does not allow it. Science does not allow you to do this kind of thing. Okay, you're not supposed to do that, not in science or physics. It's irrational. So if you want to see what a region looks like, it looks like that. Remove the hand, and now you got a region. That's what a region looks like, and that's what the region known as field looks like. It's a region of values, and the funny part is when these people, vibrate them, and they do something like this. Here, let me show you. There it is. There's a vibrating field, an excited field, you could say, okay? Because it's just a bunch of numbers, a bunch of values. And what these people do is vibrate the values. And so, we have a total irrationality with the word field. It should be eliminated completely from science. We don't need this word in physics. We don't need it for physical interpretations. If they use it in math, keep it there in math. Don't bring it into the real world. Don't bring it into the world of physics and the world of science. You want to talk about fields as a bunch of values because that's useful for you in mathematics? No problem. Keep it there. Don't cross the line into physics with the word field. Okay, so much for the field, Einstein's field, the way he explained gravity using this field concept. But Einstein did something else. He talked about in his book, right, in his book of 1917, Einstein talked about the principle of equivalence. Okay, and it's important to know again that the reason his theory was accepted, general relativity as a gravitational theory, over Newton's was because of the speed of light. Newton's equation said that gravity acts instantaneously. And Einstein said, no. You have this, both sides of his equation. On one side, you take the mass of the object, it weighs down space-time, this field, this thingy, right? Weighs it down. And because it distorts space-time now tells the object how to move. If you're walking on a trampoline, right? And you press down, well, you pushed the canvas downwards. That's what the object does. The mass, as they say, pushes it down. But now, because the canvas has been distorted, your trip is also distorted. Now you sink and your movement is affected. And that's what general relativity says in a nutshell. Objects distort the space-time, and space-time, because it's distorted, affects the movement of the object. That's it. That's in a nutshell what Einstein discovered, invented, or whatever he developed. And part of that was this principle of equivalence. He started thinking about this, and this is what he writes in his book about it, about the principle of equivalence, how he justifies it. I'm going to go a little slowly here because not everybody can understand what Einstein did with his equation, even though it's a relatively simple equation. If you had high school, you should be able to follow through, but I'll go slowly. Okay, so here it goes. He says, according to Newton's law of motion, we have, and I put the ones in red there, those are my numbers, okay, but the rest is all his. Force equal inertial mass times acceleration, okay? If now gravitation is the cause of the acceleration, he's saying gravitation is the cause, right? No, gravitation is a concept. You can't say that's the cause, but that's the language that he used. We then have force equal gravitational mass times intensity of the gravitational field. And there you see the equation on the side, okay? Force equals the gravitational mass times acceleration, okay? From these two relations follows, and he puts acceleration on one side of the equal sign and puts everything else on the other. He puts gravitational mass over inertial mass He's going to turn that into 1. He's going to say that gravitational mass is equal to inertial mass, which is what the principle of equivalence is all about. And he's going to multiply that whole factor by intensity of the gravitational field. Okay, that's number 3 there. And number 4, he just, essentially he says, gravitational mass is equal to inertial mass, acceleration being the same in both cases. So now he explains, he says, if now, as we find from experience, the acceleration is to be independent of the nature and the condition of the body and always the same for a given gravitational field, then the ratio of the gravitational to the inertial mass must likewise be the same for all bodies. By suitable choice of units, we can thus make this ratio equal to unity. He's going to say that gravitational mass, number 3 there, gravitational mass over inertial mass is equal to 1. He's going to equate those two, the G mass and the I mass, right? He's going to equate them. He's going to put that as a 1, and therefore acceleration is going to be equal to what's left, which is the intensity of the gravitational field, okay? And so he says the gravitational mass of a body is equal to its inertial mass. It is true that this important law had hitherto been recorded in mechanics, but it had not been interpreted. In other words, he's saying other people came up with this. He's saying that he's interpreting it now. He writes that in his book. Okay, so this is what he's going to prove, or he's going to try to justify in a way. He's going to give you the physical interpretation of why gravitational mass and inertial mass are equal. In other words, if you put one over the other, you get a 1. Okay, that's how this principle of equivalence was justified, and ever since, the mathematicians have been using it. Okay, so what does this mean in physical terms? Well, Einstein gave an example. He said, look, imagine you're in an elevator, right? You out in space, right? Well, you would not know if you have the simple gravity of the Earth, right? Like if the elevator is just sitting on the Earth and you drop a ball, it would fall at 9.8 meters per second square. Or if you're in a rocket that's accelerating at that same acceleration, 9.8 meters per second square. In other words, 9.8 meters per second. In other words, you're going faster and faster and faster. That's what he's saying there, right? And you can see the equations. On the left-hand side, you have force equals mass times acceleration. That is essentially if you were going with your rocket accelerating at that speed, right? 9.8 meters per second. And on the right-hand side, you have the same value, but a different equation. You have the gravitational equation, Newton's equation there. And you can see that if you take the one on the left and the one on the right, they both have the same value, 9.8 meters per second squared. So he's saying that you really can't tell the difference if you're in an elevator, whether you're accelerating away from the Earth or you're falling towards the Earth. Essentially, that was a notion he had. He says he had a vision, right? You can say thought experiment. He said, well, what if I'm accelerating with my elevator in a rocket? What if I'm falling with my elevator, because the rope was cut off or whatever? And so he looked at those, one going up, the other one going down. He says, hey, they're equivalent. Intuitively, they seem to be equivalent. And from that, he came up with his principle of equivalence, saying that he's the guy who justified it, that explained it, okay, to the mathematicians. And what's interesting, because of that, he arrives at this conclusion, okay? He's saying that if you're accelerated upwards, what happens to a flashlight that you have in your elevator, the light is going to curve. That's what he says, okay? Especially if you go at the speed of light, you accelerate at the speed of light, gravity is going to bend light, okay? And a lot of people didn't accept that until 2 years later. He says this in 1917. 1919 was a great year for Einstein. He got divorced, he got married again, and he promised his ex-wife, Mileva, that he would give her the money that he won, if he won, for his Nobel Prize, which came 2 years later in 1921. But he was already being proposed for a Nobel Prize, not for relativity. He never got a prize for relativity. He got it for the photoelectric effect, something totally different. But 1919 was a great year for him, not only because he got divorced and married, but because Arthur Eddington confirmed his theory. Okay, in other words, here we have good old Arthur Eddington, and there was this news coming up in those days, several papers. This is just one example, and where Arthur Eddington essentially, through an experiment that they did in the Pacific Ocean and several other places, they were able to measure, they were able to see, photograph a star behind the sun during an eclipse of the sun. Okay, so the moon came up there, blocked the sun. They could still see the light of a faraway distant star, right? Going around the sun and reaching our eyes, reaching the camera, right? Because of that, they said, oh, Einstein's confirmed. Einstein became an overnight sensation. Okay, as you can see, these people made a big fuss about it. Okay, says one of the most important discoveries of the century. Okay, light curves around the sun. And so, yeah, they since that, they proved it many times, they say, okay? And no, light does not curve. Light always goes straight. And if people knew a little bit about physics, right, they would know that there's this ray reversibility. The principle is called the principle of ray reversibility. Light always retraces its exact path, okay? And yeah, with the rope model, you can see why, because light has no way of getting lost, right? It just torques in situ, right? And so light goes in both directions. So it doesn't matter how much you move an atom. That's at the end of this, right? It doesn't matter where you move them. Light will never get lost because light always travels along the rope. Okay, it's a torsion. It doesn't even travel really. It's just a torsion, and you get the bumps at the end. Anyways, the point is that you can do what Arthur confirmed, right? Eddington confirmed. You can do it with straight lines. You see these patterns where you can do a curve with a bunch of straight lines, right? And that's essentially what is happening in real life. Okay? At least that's our position here. So what happened? They confirmed Einstein. Einstein became a sensation, right? And because of that, today we have all these people who measure what Einstein predicted, which is that the principle of equivalence, that inertial mass is equal to gravitational mass and vice versa. And so what they do today is measure, and they say, let's see how close we can get it. You got all these tests, all these measurements that they've taken. This is out of the Wikipedia, by the way. And all the tests that they have done year after year after year, right, where they go to ever finer, more decimal points. I measure the table, and I say, look, the table measures 1 meter, right? And the other guy comes over and he says, no, Bill, you're wrong. I measured it with a better caliber, and I found out that it's 1 meter, 1 micrometer, 1.1, 1.0001, right? So he measures it more accurately. And what they're doing is measuring it to more decimal points. And I would suggest to all these people, they stop measuring it. Why are they measuring? This is it's a conceptual issue, subtly conceptual. All you have to do is understand why, and then you don't need to measure ever again. And here you have some of the experiments that they're going to be doing in the future. Experiments are still being performed at the University of Washington. Future satellite experiments will test the weak equivalence principle in space to much higher accuracy. And they have all these tests, all these proposals, right, of how to measure, inertial and gravitational mass ever more precisely. And I'm saying, why are these people measuring? Don't they have anything better to do? I mean, what's the point of all this measuring? And people might say, well, Bill, you don't agree with the principle of equivalence. You say it's wrong, it's inaccurate, it's not perfectly equivalent. What are you saying? No, let's make it absolutely clear. The principle of equivalence is perfect. There is perfect equivalence. You don't need to go to more decimal points, please. Its principle of equivalence says that inertial mass is equal to gravitational mass. It had better be. It had better be, okay? We're talking about the same thing. So inertial mass and gravitational mass is the same thing, okay? So we don't need to measure anymore. Take it from me, they're equal. They're exactly equal. They can't be anything else. And so for this, you need to understand why. And once you know why, we're done with physics. We don't need to keep measuring and getting more equations. Totally irrelevant. We can do this simply by understanding why it's the case. Okay, so that's what we're going to look at now. And there's a couple things that we got to challenge about the principle of equivalence. Let's go with the first one, and so that we get the rules straight. First one is that there are no principles in science. Okay, principles are stuff invented by the mathematicians. They invented axioms, all kinds of words that they use there. Axioms, principles. What other one? Well, another one doesn't come to mind right now. But the issue is there are no principles. Oh, the other one would be principle, right? There are no such things as principles in science, in physics. That's stuff that belongs exclusively to mathematicians, okay, not to science and physics. Principle may relate to fundamental truth or proposition. We have no truths in science. There are no truths. Okay? Truth means I shoved my theory down your throat. That's what truth means. That's what proof means. That's what evidence is all about. That's why they do experiments, to collect evidence so they can shove it down your throat. So in science, we don't do that. In science, we explain, you understand, we're done with science. What continues is known as religion. You can believe in whatever theory you want after that in the comfort of your own home, okay? And so you have those definitions there, the other one from the dictionary.com. A fundamental, primary, or general what? Law. No, we have no laws. Okay, that was another word that I missed. Laws, truth, none of that belongs to science. We don't have laws in science, okay, that we follow or that we disobey. Any of them. We don't deal with laws, okay? Laws, they're referring to mathematical equations. They say, oh, the law, diameter is equal to circumference, or you can say circumference divided by diameter gives you 314 pi. That's a law, you can say. Great. Or maybe it's a principle because I think they haven't found the last decimal point. So meanwhile, it's a principle. No, it's all nonsense. Absolute nonsense. We don't have laws in physics. In physics, you explain, the other guy understands, we're done with physics. Okay, so we need to know how these words enter physics and why they should be banned. They have no place in physics. Okay, what we need to do is, another thing is understand what it is that we're trying to get. What is this equation? Force equals mass times acceleration. What are we analyzing? What's in front of us? Okay, and so here we start there. We have force equals mass times acceleration. That mass there, what is that? Well, that's an object. That's what it is. In this case, I'm going to put an asteroid. Okay, so we have a little asteroid or big asteroid, I guess. That's an object. That's a noun. Okay, that's a thing. Okay, that's what the mass represents. Okay, so we got that so far. Let me remove this. So we got the object. Okay, now what's that thing called acceleration? Okay, and acceleration goes like this. It's what the mass does, what the object does. Okay, in this case, the asteroid is flying towards the moon. Okay, we can watch it move. Okay, it's all there in front. So we have both words kind of accounted for. We have the mass, the object. We have what it's doing, which is the verb there, the motion of the asteroid. So the first one we can see and say, okay, that's an object. That's a thing. It's got shape. No problem there. The other one, you have to watch the movie. You have to watch the movie of how the asteroid, goes towards the moon. Okay, so far so good. What's the issue? The issue is the other word. This is the word that we have problems with, the word force. Now here we have a real problem because force we can't see or touch, and we don't see it there. All we see is we see the asteroid, we see the motion, the acceleration, or how it approaches the moon, the speed or the motion, etc., right? But we don't see any mediator, and we don't see what's causing this whole thing. And that's what the word force represents. Okay, the word force is the big problem here, and we need to account for that in order to understand, what's going on here, in order, especially to understand the principle of equivalence, right? Okay, so let's move on here. We're going to look at this word force, and here we have the principle of equivalence. I just want to make sure that we understand inertial mass is exactly equal to gravitational mass. So I'm not disputing the principle of equivalence. I'm disputing Einstein's explanation, his justification for this equivalence, and also criticizing the mathematicians of the last 400 years because they simply had something wrong. And that's what I'm going to go over right now. Here we have the gravitational force, okay? And you can see that this is what they do. They put force equals mass times acceleration, and they make it equal to force equals to the Newton's gravitational equation, which is force equals gravitational equation, mass times mass divided by distance squared. And that's a no-no. That's wrong. Okay, that's simply wrong. So they've been doing this for 400 years. They've been doing it 400 years. They've been doing it wrong. Okay, and so we start with there. You see, force equals gravitational constant g, mass over distance squared. What's wrong with that? Well, what's wrong with that is this. Okay, we have to remove the word force. It's not a force. Okay, it's weight, and weight is not a force. You don't have to move in order to have weight. You have weight anywhere around the earth at a location. In fact, that's what the word field means. The word field means that you have gravitational field. We'll just use that and forget about the magnetic field or electric field. If you have a gravitational field, what is a gravitational field? It says that at each point in space you have a different value. Each point meaning every location. You move a picometer and you already have a different weight. That's how fast gravity is. It's faster than light. It's like instantaneous. I hate the word instantaneous because instantaneous, again, we have a problem with that because instantaneous requires two frames of the universal movie. Even if you chop motion or time as many times as you want, you'll never arrive at one frame of the universal movie. You will always have two frames. Why? Because motion is defined as two locations, and so is time. Time requires two locations. So you need two frames of the universal movie. No matter how much you chop motion and time, you'll always end up with two frames of the universal movie by definition of the words motion and time. Okay, period. And so the issue here is that, that equation is the equation of weight. Okay, it's the equation of weight. And weight is a static concept, and it's a tension, because that means I can take a snapshot of you at some point around the earth at a given location. You already have weight there. It's a snapshot. You didn't have two frames of the universal movie or more. In a single frame, you have location, you already have weight. There's a weight with you for you with respect to the earth. Okay? So you already have weight. I can, if I could freeze the entire universe, weigh you there and give you a value, I could give you a value and say, here, you at this location, this is how much you weigh. If you're farther out or closer, all bets are off. But at this location, this is how much you weigh. And as soon as you change location, well, you change your weight. So weight is location specific. And that's what Newton's equation says, because it's got distance in the denominator. And we're going to look at that distance because that's kind of suspect, that little distance there. But we're getting ahead of ourselves. So it's a tension. Tension is not a force. Okay, that's what you need to understand there. Tension is not a force. Tension is a static concept. Force is a dynamic concept. No mathematician ever discovered that, because they talk about the tension on a string, saying, oh, you have to pull on a string. Not in tension. Tension, in tension. Not with tension. Tension means that no one wins the tug of war at that moment in time. Okay, so you can represent tension in a single frame of the universal movie. The way we do it, we put a dumbbell, two atoms bound by a stick. Stick made out of a single piece. It doesn't stretch. It doesn't shrink. That's tension. Tension is a stick made of a single piece. That's what tension is. It's not pull or push, okay? And that's where these people, because they never paid attention to qualitative concepts or introduced them into their analysis, they ended up with quantitative analysis, and from there they ended up with tension being, a value, a number, and therefore it's governed by push and pull. That's how they ended up with that. Okay, so what's the issue? The issue is we're going to replace that force, right? We're going to replace it with tension. And of course, when you do that, then you reach the conclusion that this is not true. Okay, that force equals mass times acceleration is not equal to tension equal to Newton's equation there. Okay, so that's why they're not equal. Okay, in other words, you're talking about two different things. Does this mean that the principle of equivalence is wrong? No. In fact, this confirms that you don't need to measure anymore. They are perfectly equivalent. Okay, and that's what we're going to show now. Okay, let's move on here. Give me a second. Okay, so here we have an example, so we can get into the things here, into the what we're trying to show. Okay, here we have an asteroid, and it's falling towards the Earth, the one on the bottom. The one on the top is not, because it's just static there. Okay, so that one on the top already has weight. Okay, whereas the one on the bottom is moving towards the Earth, and it's a little different process than the one on the top. And why the difference is that little d, the little d like David, distance. The distance on the top is separation, whereas the distance on the bottom is distance traveled. And these people have confused a dynamic concept such as distance traveled and confused it for, a static distance. That's where the problem is, okay? And so we first have to understand that these two equations talk about two different things. The one on the top talks about tension. Distance is distance of physics, meaning separation. We don't care what the number is. It doesn't matter. Mother Nature doesn't deal with numbers. Mother Nature just says the asteroid is far away from the Earth, or the moon in this case, and we have separation, and that asteroid already has some kind of weight. Okay? There's a force acting upon it, you could say, but it's got weight. And the one on the bottom is totally different. That one's it's just the acceleration there that you see there. That includes distance traveled. Okay, that's what the difference is. And here we can see it. Okay, the difference between this. This is a summary. Let me show this. What you got here is weight versus acceleration. The acceleration is the one from Newton's second law, force equals mass times acceleration. The weight is the one on the left, which is really a tension. And what is the difference? Well, in the first one, you can see the distance is static. In the second one, distance is dynamic. Distance is traveled. Okay, it's a number. Distance is between two objects. The distance here is the one traveled by the object. That's, in other words, the object has a starting point. From there, it moves forward. Okay, and because it's moving forward in its forward direction, it's moving, and it's a distance traveled from that point, from its the starting point. That's different than the other one, which is a separation between two objects. Okay, each frame in the movie depicts a static distance. All you have is just two objects there separated by space. The second one, each frame in the movie is a cross-section of the itinerary of one object. In other words, if you put all these frames together, you get motion. But in a single frame, all you have is that. You have just the distance is decreasing in the direction of where it's going and increasing behind it. Okay, so what you have is that separate. In other words, it shows a distance traveled. Okay, and then here you have distance decreases, d1, d2, d3, when acceleration increases. Okay, and the other one's in reverse. Distance increases when acceleration increases. One case it increases, and the other one decreases. Okay, the other one, the next one there, distance is towards the other object, distance is away from an unspecified object. And that's, again, when they move. But again, we're talking about static distances in the case on the left. But if you put several of these frames, then, 4, 5, and 6, and 7 apply. Distance is a measure of weight, whereas the other one, this is a measure of velocity. Okay? And then force increases when distance decreases. Force increases when distance increases. Okay? So you can see that these distances are not the same, but they treat them as the same, and they always put acceleration equal to whatever's on the other side of Newton's gravitational equation. That's not right. You can't do that because you're not talking about the same distances in these two cases. Okay, they're two different distances. The one on the left, the one for weight, is the distance of physics. It's separation. We don't care what the number is. Mother Nature doesn't know math, right? Never did math. And so what can I say? She never went to school, never learned how to do numbers. All she does is have objects and atoms. That's what she works with every day. And you have to be able to explain physics with just that. No numbers. We don't need numbers in physics. All we need to do is explain what's happening out there in the universe. Why, what causes a pencil to fall to the floor, for example. That's a physical phenomenon. And I don't need any numbers to explain what caused that to happen. And that's what Mother Nature understands. Mother Nature and Father Universe, all they do is move atoms from one place to another. They know nothing about math, about how fast or how much. They don't care about that. They don't deal with that stuff. That's us, humans, right? That's why these people have the numbers, but they don't have the explanations. Okay? Okay, so we got to find out what this distance is. And when you look up, you get scared because you find out that they never defined the word distance. Okay? They don't know what distance is. And you can see why. It says the distance between 2 points in physical space is what? The length. Now, length is not distance, and distance is not length. Why did they put the word length in there? And you can see there, length is a measure of distance. So when you look up the word length, it says it's a distance. When you look up distance, it says it's a length. Why? Well, because they're not talking about either length or distance. They're talking about distance traveled, about unrolling the tip of the measuring tape. So they say, how many meters? That's what a mathematician wants to know, and that's distance to him, right? But that's not this. Distance is just separation. I don't need any numbers to have the notion of distance. But if you want to measure the distance and unroll your measuring tape that you have already created a standard, the meter or the centimeter or the, the yard or the foot, you unroll the measuring tape, it's so many feet or so many meters. Okay, what did you do? You're unrolling something. You have a dynamic concept. What you have is the unrolling of the tip of the measuring tape. You're putting tiles on the floor. You create a tile, say this is the meter, and now you're putting tiles on the floor and counting all the tiles. That's different than saying there's a separation between two mountains, for example. Okay, and so the problem is that they define distance in terms of length, length in terms of distance. Why? Because to them it doesn't matter. If you're going to measure distance, like between the Earth and the Moon, you unroll the measuring tape or whatever thing that you use to measure that, and you just count and you say this is the number. This is how many kilometers. And if you're going to do length, the length of the table, the same thing. You unroll your measuring tape. So whether you do one thing or the other, you're always unrolling the measuring tape. But that's distance traveled of the tip of your measuring tape or counting tiles or however you want to visualize that. That's not separation, physical separation, qualitative separation. Okay, and that's where the problem is. These people had no idea of these qualitative notions, and that's why they confused the two distances. And so here we have the rope model, right? You have an asteroid, and it's at a distance from the moon in this case, and there's so many ropes. Every atom of both objects are connected to all the others, but we're only going to use one atom from the asteroid, and well, you can imagine all the ropes connected to every atom that constitutes the moon. Okay, but here we put only one atom. Okay, what's going to happen? Well, we're going to have this situation where the one on the bottom, right, is going to be approaching the moon. okay? And so we can see what's happening here with the ropes, okay? As it approaches, the ropes fan out, and this is the acceleration of gravity. But you would have to watch a movie in order to understand it. You have to record each one of the locations of the asteroid in order to conceptualize this, okay? So this is what we're suggesting. We're saying that every atom of the asteroid is bound, physically bound to every atom of the moon and vice versa. And as they approach, what you have is the ropes fanning out, and that explains the acceleration of gravity. Okay, so now we have a mechanism for the acceleration. What happens to the ropes? Well, let's look at it one frame at a time. Okay, here's the first one. Okay, you can see it gets closer. What happens to the ropes? They fan out. As it gets closer, what's happening next? Well, again, you can see they fan out, and they keep fanning out the closer they get. That's what's happening. Okay, so you can see how in other words, the asteroid really is not being pulled by the moon. What's happening is the ropes are fanning out as the asteroid gets closer and closer to the moon. So the asteroid is just drifting towards the moon, and the ropes fan out as it gets closer. And that's why it's a distance-related phenomenon. You know, the farther it is, the more distance, right? The denominator of Newton's denominator, the distance there is bigger. And being it bigger, the force is lower. And vice versa. When the distance is less, you know, the force increases. That's what's happening. That's just as simple as that. And so here we have different versions of this. You see when it's very far away, like on the bottom there, you have maybe it's 1 kilogram when it's at a great distance. Why? Because all the ropes come together, right? And as the asteroid approaches the moon, you can see what's happening. It goes from 25 tons, 200 tons, 500 tons, 1,000 tons, the closer it gets. Why? Because the ropes are fanning out. And what we're saying here is that weight, right? Using Newton's equation, weight is a function of how many ropes act independently. Okay, that's what it's all about. How many ropes at a given location. And of course, if you take all those locations, put it in a movie, then you're going to get the acceleration of gravity. Okay, so that's what we're saying. And that's the illustration of gravity. You can see we can illustrate gravity in a single, or weight in a single frame, because all you need to know is how many ropes are converging upon that point. Okay. And here you have it. Okay, you have Einstein versus my version. In his version, he says, well, I don't know why, but every time we measure, we find out that whether the rocket goes upwards, you know, the acceleration, 9.8 meters per second squared acceleration, it's very similar. You wouldn't be able to tell the difference if you're falling to Earth at with gravitational acceleration, or if you were going at 9.8 meters per second square away from the Earth. In this case, you have force equals mass times acceleration on the left, and you have Newton's gravitational equation on the right. But see, with the rope model, you can finally visualize why it's the case. Because if you take a single atom, right, a single atom at a given location, right, it doesn't matter if you're going outwards or coming towards the Earth. At that location, they both have to match. And we're talking about a single atom here, okay? And so here, let me illustrate that so that you can get an idea, better idea what I'm talking about. Here it is, okay? We have a single hydrogen atom, just one hydrogen atom, okay? Weight is the number of ropes, effective ropes. Ropes that have separated from, you know, the axis, the main axis. If they separate, you have, you know, they're not on the same axis, suddenly you have more effective ropes. That's what we're saying here. The closer you get, more effective ropes. The farther you get, the fewer ropes that you have. That's what it's all about. And weight is simply how many ropes at a given location. Here you have an atom, a hydrogen atom. It doesn't matter what it belongs to. Could belong to anything. It's at a given distance, right? You have all the ropes from every atom on Earth converging upon that atom, okay? And so it doesn't matter if the atom belongs to a feather or to an elephant. It doesn't really matter, because as long as it's a hydrogen atom, in this case we're talking about hydrogen atom, it's got a single rope connecting to every atom, hydrogen atom constituting the Earth. Okay, it's more complicated when you talk about other atoms like carbon or iron or whatever. But the point here is the following. With that atom there, you don't know if it's leaving or coming, because at that point, force equals mass times acceleration is equal to tension equal to g mass 1, mass 2 over distance squared. At that location, they both have to be equal because it's the same number of robes converging upon that atom at that location. That's why the principal equivalence is correct in that sense, okay? It is at that point the same value, okay? So yeah, if you were to calculate with just one value, force equals mass times acceleration is equal to tension and what's on the right-hand side there, okay? That's what we're talking about. Okay, so someone might ask, well, Bill, what if I come at a certain speed at that location, okay? For example, you have, all these atoms, right? And they're connected to the Earth, right? And at that location, there's so many ropes connecting one atom to every atom on Earth. Now, would it be the same if you come at a great speed to that same location, you have the same number of ropes, but does that thing weigh the same? You see the problem? And here, let me illustrate it for you, what I'm saying here, the question. Okay, here you have an elephant, okay? We're going to weigh the elephant. Better yet, we're going to weigh a single atom, hydrogen atom, of the elephant, okay? So let me illustrate that so you see where I'm going with this train of thought. Here it is. Okay, we have a single atom, and at that location, right, that atom has so many ropes converging from every atom on Earth to that atom, okay? So is that elephant going up or is that elephant coming down? That's one issue, right? And I'm saying at that location, that atom doesn't care. That atom has a single value, okay? And that's the weight of that atom at that location. But what happens if the elephant is falling now? And I'm going to put them side by side just to show you, but it's the same elephant, the same location, okay? Except that one is falling, on the scale, and the other one is just sitting there. You're just weighing them, So the one on the left, you can look at it as a static scenario, and the other one is a dynamic one. Would they weigh the same? I mean, the number of ropes converging upon that atom that we just mentioned has to be the same, right? For example, here, let me illustrate that. Okay, that atom is the same. Again, keep in mind they're at the same location. I just put them side by side so you can see what I'm comparing here. In the right-hand side, we have the elephant falling, and the other one, just static. But at that location, that atom has only a certain number of ropes converging upon it from every atom on Earth. So do they weigh the same? One guy falling, the other one just sitting there, right? And the answer is very simple, really, to that question. Let me put this up here. You're comparing apples and oranges. In one case, you're comparing weight, okay? So even though you have at that location, all the ropes converging upon that atom, in one case, you're comparing weight against force because this guy is falling. You're comparing one frame in the Universal movie where the guy is falling. And obviously, you're not comparing now apples and apples. You're comparing apples and oranges. What you have is distance traveled. You have force equals mass times acceleration that you have to add on to that. Because you're not talking, because if I only look at the number of ropes, that's a static scenario, there's no motion. But you're talking about motion that took you to that position. And so you have to add that motion to the number of ropes, okay? Because you're talking about something else. You're talking about the distance traveled now again. And so again, you need to keep in mind what we're talking about here. One is distance separation, the other one is distance traveled. If you're going to talk about distance traveled, you cannot compare it against the distance of physics, which is just separation. So we have to keep in mind what we're talking about here at all points in time. You cannot include the distance traveled of mathematics with the distance of physics. Okay, if you're going to talk about weight, okay, then you're talking about separation, and for that you don't talk about what happened in the previous frames of the movie. okay, which is what you're doing if you include the travel of the elephant falling towards the scale. Okay? In fact, you can prove this at home, always in the presence of a trained relativist, just sit on the scale or stand on the scale, check your weight, and then jump. You'll see that the numbers will go higher, okay? And so you say, well, hold it, isn't it the same number of ropes? Yeah, but you're comparing apples and oranges. You're comparing distance traveled versus distance. And so unless you understand that, yeah, you'll reach the wrong conclusion. Anyways, here we have a notion that I presented in the past, which is the universal movie. And what you have in any frame there is every atom at a given location. That's our universal movie. In a single frame, just all atoms in the universe. And every atom has a certain distance, a certain location with respect to all others. Okay, that's what it's there. What do we have? We have weight versus acceleration. Okay, and acceleration is a dynamic concept, whereas weight is a static concept. Weight, you do not need to move anything. You already have weight at any location around the Earth. So we can represent weight in a single frame of the universal movie. And here, let me show you that. We have the elephant there. We have a single frame. And what is weight? Weight is all the ropes converging upon an atom. And so that's weight as far as the rope model. You don't need to have anything moving. You already have weight anywhere around the Earth. Okay. Okay, so yeah, weight is a static concept, and all I can say is, all these people who are developing equations, like for dark matter, black holes, wormholes, dark energy, Big Bang, all this nonsense, they're wasting their time. They just as well could be, developing equations for leprechauns and unicorns. Or ghosts or whatever. What's the point of, what are they doing? What are these people inventing equations for? They're making money. You're paying them to develop equations for inexistent stuff. Nonsense, simply because, they say, well, it's invisible and it's intangible. Yeah, so is the rope, but the rope is a physical object. A black hole is not defined as a physical object. Neither is a wormhole. Neither is dark energy or dark matter. None of them are defined as physical objects. So these people are having concepts, and that's what they're developing. They're developing equations for concepts because they're going to use the concept to say, well, the black hole moves a star around. So he's going to use it as a physical object, but it's a concept. It's a mathematical concept. That's all it is. And it's when they reify, convert these concepts into object that we run into trouble. Okay, just to end the day today, I just want to show you something. All these mathematicians, what they do, because they do all day long is math, right? Except the celebrities, they go out there and they try to peddle their theories, their physical interpretations to the public. Makes no sense. But that's what they do all day long. They don't do equations when they talk to the public. And when you put them against the wall, they say, well, all we do is equations. And so to show that they're intelligent, what they do, they take pictures in front of boards full of equations. And here you have one fellow, his name is Ed Witten, and he's a famous strength theorist. And he does equations. You can see he's taken pictures of himself with all the equations in the background to show how intelligent he is. Oh man, it's scary, right? If he can read all those equations, he must be intelligent, right? And so that's what they do. They put all these equations in the background and say, hey, look how intelligent I am. And what they're doing is doing equations for dark matter, Big Bang, dark energy, all these spirits and ghosts that they study every day. Here you have another fellow. He's also a strength theorist. His name is Leo Susskind. And you can see he also has equations in the background, and they all put equations out there to show you how intelligent they are. Here you have another one. Her name is Sabine Hassenfelder, and she has a picture taken in front of equations. Okay, and does this make them intelligent? The fact that they have all these equations in the background, does that mean that they're intelligent people? Is that a sign of intelligence? The fact that they've got equations back there, maybe the janitor wrote those equations. They just took the picture, for all we know. Here you have Neil Tyson. Let me show you him. And he's got also equations on the board. He looks so smart, right? Yeah, all these people, they brag about how they know all these equations. You don't. And because of that, they have the right to convince you that their theories are correct, even though they don't understand that they can't explain them, but they say they know it all, right? And here you have Brian Greene. He's also kind of in a trance there, showing how smart he is, because of all those equations that he's got behind him. And they put all these pictures out there, of how intelligent they are just by putting all these equations. And so one question you should ask yourself, here you have, because after all, math is just a language, right? That's all it is. And here you have a language, okay? Here you have this fellow, and his name is King Tut. And he took a picture in front of hieroglyphics. Does that mean he was an intelligent fellow because he knew how to read all that stuff, that language, okay? And here you have another fellow. He's a little more closer to our days, and he also put equations on the board, I guess. I don't know what they are. A bunch of hieroglyphics. His name is Mao Zedong, and he can read all that stuff. I can't. So does that make him intelligent because he knows a language that I don't? If you learn Chinese, does that mean you're an intelligent person because you know how to read those hieroglyphics? So, what I did was, I decided to show that I'm intelligent too, So I went out there and I said, I'm going to take a picture in front of equations too, and just to show you that, I'm just as intelligent as all of them. And here it is, the picture I took. There you have it, okay? I also know equations, okay? So there's my picture, and please spread it around, okay? And so hopefully they'll consider me intelligent too because I've got equations as well. With that, I'll see you next week. Bye-bye.